Welcome to This Explainer. If you've ever flipped up in a chemistry textbook and just felt totally overwhelmed by all those random letters and tiny little numbers, trust me, you are not alone. A lot of people see it as a super intimidating math problem, but today, we're going to flip the script on that completely. Let's think of chemistry not as math, but as a fascinating secret language that's just waiting to be decoded. Honestly, it's exactly like learning any new language. Once you pick up a few basic vocabulary words and figure out a couple of simple grammar rules, a whole new world opens up to you. You'll actually start to see the hidden structure of literally everything around you. By the end of our time together, you're going to be reading these chemical codes with absolute confidence.
So here's our roadmap for today. First up, we'll explore the magic of compounds. Second, we'll learn the grammar of naming them. Third, we'll visualize these words with particle diagrams. And finally, we'll decode the chemical formula themselves. Let's jump right in.
All right, kicking things off with Section 1, the magic of compounds, and how elements actually transform.
Okay, look at this stark, honestly kind of magical contrast. On one side, we've got sodium. It's a highly reactive metal. Right next to it, chlorine, a toxic gas. You absolutely would not want to eat either of those, right? But when these two specific elements react and bond together, they transform into something completely new, sodium chloride. That is literally just common table salt. A totally safe, everyday thing you probably put on your fries. It's an incredible transformation.
And that actually brings us to a crucial definition in our new language, a compound. So a compound is a substance where two or more different kinds of atoms are joined tightly together through bonding. And bonding, that is the absolute secret ingredient here. It's just the chemistry term for atoms joining tightly. When different elements bond, they completely lose those original individual properties. They become something entirely new with completely new properties, just like that highly reactive metal and toxic gas turning into totally harmless, delicious salt. So just to really lock in this foundation, let's briefly contrast elements and compounds. An element, like what you'd see on the periodic table, is pure. It's made of just one single type of atom. A compound, though, is a combination. It happens when two or more different types of atoms are locked tightly together. You can think of elements as the individual letters of an alphabet, and compounds, well, those are the words those letters spell out when combined.
Moving right along to Section 2, naming chemical compounds, or as I like to call it, learning the grammar.
So scientists actually use some pretty specific grammar rules to name these new compounds. Here's how it works. If a compound has a metal in it, the metal's name goes first, always. The nonmetal comes second. But here's the fun little grammar twist. The ending of that nonmetal gets swapped out for "ide." That is exactly why mixing sodium and chlorine doesn't give us sodium chlorine. It gives us sodium chloride. And hey, if a third element sneaks in there, specifically oxygen, that ending usually shifts again to "ate."
Okay, let's actually test this out. Imagine a student writes down the name sulfur calcium for a compound made of, well, calcium and sulfur. What exactly is wrong with that? Think about the rules we literally just talked about. Calcium is the metal, right? Sulfur is the nonmetal. According to our chemistry and grammar, the metal has to come first. Plus, the nonmetal needs that "ide" ending, so the correct scientific name is actually calcium sulfide. See, you're already speaking the language.
Now check out these really beautiful blue crystals. This is copper sulfate, and it perfectly illustrates that final naming rule we mentioned about oxygen. Just by reading the name copper sulfate, you can decode exactly what's hiding inside it. Copper gives us the metal. Sulf tells us there's sulfur. But what about that "ate" ending? That little suffix is a huge clue. It tells us that oxygen is in the mix too. Copper, sulfur, and oxygen all bonded together into one package.
All right, on to Section 3, visualizing particle diagrams. It's time to start picturing the words.
Before we jump into the raw math, we really need to picture what these chemical words look like on a microscopic level. Take a look at these particle diagrams. Sometimes, the name of a compound literally spells out exactly how many of each atom are bonded together. On one side, we have carbon dioxide. Di literally means two, so that's one carbon atom joined to two oxygen atoms. On the other side, carbon monoxide. Mono means one, so it's one carbon joined to just one oxygen. Seeing them side by side like this, it really makes the difference crystal clear.
Now, scientists use a couple of different ways to visualize these bonds. We've got physical 3D ball and stick models, and then flatter 2D particle diagrams. But honestly, whether you use a physical model or a simple flat drawing, they both do the exact same important job. They help us easily spot if a substance is a compound. How? Just look at the colors and labels. If you see different kinds of atoms, like say, a black carbon circle bonded to a red oxygen circle, boom, you know instantly you're looking at a compound. And here we are at Section 4, Decoding Chemical Formula. It's time to start reading the math. This is the big payoff. This is where we put everything together and read the actual mathematical symbols like fluent speakers. So every compound has an everyday name, a chemical name, and a formula. The formula uses the symbols of the elements. But the real secret to reading a formula? It's all in the subscripts. Subscripts are those tiny little numbers written down below and to the right of an element symbol. Think of them as the quantifiers in our secret language. They tell you exactly how many atoms of that specific element make up one single particle of the compound.
Now, here is a super fascinating little quirk of this language, and you absolutely have to remember it. I call it the invisible one rule. If you're looking at a chemical symbol in a formula, and there is no tiny number next to it, it does not mean zero. No way. It actually means there is exactly one atom of that element present. So the golden rule here is, no number means 1. It's that simple.
Let's put this into practice and decode this table together. Take hydrogen sulfide, H2S. That little subscript, 2, tells us we've got 2 hydrogens, but look after the S. There's no number, so our invisible one rule kicks in. That means just 1 sulfur. Make sense? Okay, let's try a tougher one. Calcium carbonate, CaCO3. No numbers after the Ca or the C, which means exactly 1 calcium and 1 carbon atom. But then we have that O3. That means 3 oxygen atoms all locked together in this one particle. Seriously, you are officially reading chemical formulas now.
Just a quick, helpful little tip as you get the hang of this. In chemistry, a single letter changes absolutely everything. You have to be super careful when reading these symbols. For example, whatever you do not confuse the symbol for carbon, which is just a simple capital C, with the symbol for calcium, which is a capital C followed by a lowercase a. Paying really close attention to exactly how these symbols are written is absolutely vital so you don't accidentally mix up your ingredients.
To wrap up everything we've uncovered in this explainer, I want to share this core quote from our source material. It says, "Chemical formulae represent the number of atoms present in a compound through the use of element symbols and small numbers known as subscripts." And you know, that really hits the nail on the head. You've seen how elements completely transform when they bond into compounds. You've learned the grammar of using "ide" and "ate." You've visualized the molecules, and now you literally have the skills to translate these symbols and subscripts into real-world atomic ingredients.
So I want to leave you with a bit of a challenge. Take a second and just look around the room you're in right now. Every single object you see, the water in your glass, the salt in your kitchen, literally the air you're breathing out, it is all built from these bonded elements. So what secret chemical codes and formulas are just waiting to be cracked in your everyday life? Now that you know the language of elements, compounds, and subscripts, you hold the key to decode the entire world around you. Keep looking, keep learning, and as always, stay curious.